Well, hi again, everybody. And this is going to be the second module in a series of modules I have planned for the second law of thermodynamics. This module also, I do not expect it to be easy because we're going to introduce the idea of entropy. And also, there are three statements of the second law of thermodynamics, not just one. So those certainly are complications that can be difficult. So let's see what we've got. And nowadays, there's a lot of talk about anything is possible. If you can dream it, it can become possible. I'm going to have to tell you, I hate to break your heart, but that's simply not true in the engineering and scientific world. And so I put a big question mark next to the big anything is possible icon, as well as our friend Lee Corso, who would respond to the meme anything is possible, probably with not so fast, my friend. And that's one reason that you're taking this thermodynamics course, is that you're developing skills as an engineer to be able to analyze proposed things, proposed ideas of anything is possible. And you are going to be able to quantify, yes, that is possible. Let's pursue that idea. Or, I'm sorry, that idea simply is impossible. And so not so fast, my friend, not anything is possible. And you're headed in a direction where you're going to be able to quantify that, yay or nay. The next slide starts with, and now something for something completely different. And this quote is attributed to John Cleese. He was the either founding or leading member of a comedy group called Monty Python's Flying Circus when I was a college student. And my friends and I would gather together once a week and watch public broadcasting TV for a 30-minute comedy show called Monty Python's Flying Circus, probably one of the most irreverent and crazy comedy groups you'd ever want to know. So I encourage you to go on YouTube and do a little checking into Monty Python's Flying Circus. But it's certainly very appropriate to say, now let's talk about something completely different, which is entropy. And so I'll start off by saying entropy is a property. Now let's take a step back and look at properties that you're already somewhat expert at, properties we already know. And how do you visualize them? How would you visualize pressure? How do you envision pressure? I did force divided by area, a force acting over an area. How about volume and specific volume? You've got a picture of that in your head, a volume, 3 dimensions. You can count a volume. Okay, got it. A tank. Temperature. You've got a pretty good visualization of temperature. By golly, you know when it's hot and you know when it's cold. Okay, high temperatures and low temperatures. You have a pretty good feel for internal energy, capital U and little u. And you have a pretty good feel for enthalpy, H and little h. And that's basically energy content that includes flow work in it. And we use enthalpy H for open systems. Okay, now something completely different, a new property called entropy. Now, the variable names, the variable we call entropy S, we assign S as the letter that's associated with entropy, S, capital S and little s. Intensive property and, I'm sorry, extensive property, capital S, and intensive property, little s. Now, here's what I want you to visualize. If you get anything out of this video, visualization of entropy. Entropy is a measure of disorder. We're going to be able to quantify entropy later on, but not here. Okay, visualization, a measure of disorder. Okay, when S is a large value, that means the substance is more disordered. When S is a smaller value than that, then the substance is more ordered. And I want you to think in your mind, think about how do you visualize disorder and order? How do you visualize that in your head? Okay, next we go back to the textbook. How is entropy defined? Entropy is defined in an equation. So left-hand side, capital S2 minus capital S1, extensive properties at state 2 and state 1. So delta S, S2 minus S1, is the change in entropy for a system undergoing a process state 1 to state 2, equals the right-hand side. Oh boy, the right-hand side. It is an integral. It's an integral over a certain path, okay? And it's the integral of heat transfer divided by the temperature at which the heat transfer is occurring. And you have to perform this integral, these big parentheses, you have to perform the integral across a path that is internally reversible. Internally reversible. Okay, so this REV is critical in this definition. Okay, so right-hand side, the integral of all heat transfer at a reservoir temperature T, following any, but you have to follow an internally reversible path from state 1 to state 2. Okay, and so you might want to go back to the previous video where I talked about what makes a process irreversible and then what makes a process reversible. Okay, so that's the definition. I'm going to move on from here. Definition of entropy change, S2 minus S1. Next, we're going to stick in the textbook and we're going to take the differential of both sides of this equation. A little bit like taking the derivative, but we're going to take the differential of both sides so that the change in S becomes ds, the incremental change in entropy. That's taking the differential. Now, if you take the differential of an integral, you just get the integrand, right? Okay, so that's how we dispense with this integral sign, by taking the differential. And we've got del Q, the little incremental heat transfer, divided by the temperature at which the heat transfer occurs. And the path has got to be in the incremental path that has got to be internally reversible. Got to be along a reversible path from 1 to 2. Okay. I'm going to pause a little bit because I don't want to blaze through too fast. We started this integral definition of entropy change. Entropy is a measure of disorder. Okay. Okay. When I think of ordered, I think of little marbles all packed together in an orderly fashion of rows and columns. When I think of disorder, I think of taking those marbles and throwing them up in the air and they're just all over the place. That would be disorder. So that's the way I think about entropy. Order, a small value for entropy. Disorder, a large value of entropy. Okay, next slide. Still sticking with our textbook, visualizing heat transfer for a reversible process on a TS diagram. So now we've got a whole new diagram to talk about. Temperature entropy diagram, temperature on the Y, S entropy on the X. And remember, you're good at a couple of diagrams already. You're good at a PV diagram, and you're pretty good at a TV diagram. Okay. And you remember particularly how a PV diagram helped you visualize work. You remember work for a closed system was the integral of PDV. We're going to do the same exercise for using the TS diagram for heat transfer. Okay, so here we go on this slide. Here's our equation 6(2b). ds, incremental change in entropy, equals del Q over T along an internally reversible path. Okay. Next thing I want to do is multiply both sides of this equation by T. I'm going to get TDS is equal to del Q across a reversible process, del Q. That would be like a little piece of incremental heat transfer, little tiny piece of heat transfer. TdS is equal to del Q, cross-reversible process. The next thing I'm going to do is integrate both sides of this equation from state 1 to state 2. So left-hand side, the integral from state 1 to state 2 of TdS equals right-hand side, the integral from 1 to 2 of del Q, of incremental Q. Well, we can do the integral of the right-hand side immediately if we integrate across the entire process of del Q. That's just Q. That's just capital QN, okay? And let's call it QN reversible. So let's call it QN to a closed system, QN reversible. All right. Now, so the left-hand side, look, let's think about what an integral means on a TS diagram. So here's my TS diagram, screenshot right from the textbook, T on the Y, S on the X. Here's some crazy process 1 to 2, but we're going to say it's reversible. We can describe it by a path. We can describe it by a uniform line, a uniformly drawn line. It's a curve. It's just some generic reversible path from 1 to 2. Let's visualize what's the integral of TdS. It's like the integral of y dx. It's the area under the curve. And so visually, the shaded area under the curve for this reversible path, 1 to 2, is the heat transfer. So Qn is the integral. The left Qn will be positive when you're integrating left to right. Cool. That's a big takeaway. This is an important slide. Okay, so just remember in your mind the things you're trying to pick up from this video. Draw a TS diagram can help you visualize heat transfer for any reversible process. Any reversible process, visualize heat transfer on a TS diagram. So what's it? Let's go back on things you've already mastered. On a PV diagram for a closed system. PV diagram, closed system, the integral of PDV is the work out. Okay, trying to put all this stuff together. We're putting all these things together in one monstrous, difficult thermo course. Okay. Okay, that's your crash course on what is entropy. That was something completely different. Now, the purpose of this video, there's three separate statements of the second law of thermodynamics, and we're going to go through them, 1, 2, 3. In your mind, can you think of the one statement of the first law of thermodynamics for a closed system? First law of thermodynamics, closed system. You got that in your mind? Okay, now let's move on to the second law of thermodynamics. Much more complex because there's 3 statements of it. Okay, first statement is called the Clausius statement, the Clausius statement of the second law. I'm going to have to just read it to you off the slide. It is impossible for any system to operate in such a way that the sole result would be energy transfer by heat transfer from a colder body to a hotter body. That's the statement. Now, let's look at what this means in a schematic. So impossible. Okay, so my left schematic, it's impossible. This is impossible. What I'm drawing here is impossible to transfer heat from cold to hot, TL, T low, TH, hot. Okay. I'm showing heat transfer going upwards from cold to hot. And I'm saying that any type of power associated or work or power associated with this is 0 because it says the sole result. Now you're thinking, a sharp student is saying, wait a minute, I just came from the refrigerator in my kitchen. I'm transferring heat from cold to hot. I'm transferring heat from my freezer department out to the surroundings. There's hot air coming out of the back of my refrigerator. I'm transferring heat from the ice cubes into the surroundings. Why? So is this guy lying to me? No. So here is a sketch of what your refrigerator looks like. It's a system operating in a cycle with refrigerant, okay? We are running a compressor. We're running a piece of equipment within this closed system called the compressor. We have to purchase energy to do that. And that's what enables us to transfer heat from cold, freezer, to hot surroundings in the kitchen. This is called a refrigerator. Okay. It's possible, but you got to invest some work. Okay. Let's recap the first statement of the second law. Clausius statement. It says it's impossible to transfer heat from cold to hot only. Heat doesn't flow from cold to hot on its own. Now let's the real world. Engineers can make heat flow from cold to hot, but it costs you some power. And that's the power of taking this class. Engineers learn how to transfer heat from cold to hot by investing power. Okay, we're 1/3 through. Second statement of the second law. Okay. It's called the Kelvin-Planck statement. And for those of you that find this stuff interesting, you find it challenging, you're thinking about going to graduate school, you're going to talk a lot about the Clausius inequality, the Clausius statement, the Kelvin-Planck statement. We talk a lot about that in graduate school. But for right now, we're just going to call it the Kelvin-Planck statement. Okay, here we go. I'm going to read it. It is impossible for any system to operate in a thermodynamic cycle, and deliver a net amount of energy by work to the surroundings while receiving energy by heat transfer from a single thermal reservoir. Here's what this means. Here's what this Kelvin-Planck statement means in a schematic. It says you can't receive heat transfer from a high temperature reservoir and operate in a cycle and make power, and that's it. You can't transform heat directly into power. Okay, that's what that means. So this is the sketch. It is impossible because of the second law. Okay, you can't operate in a cycle and turn heat directly into work. Okay, this is just a simplifying statement, not as fancy a statement, but it restates the Kelvin-Planck statement. But you say, wait a minute. I've toured power plants. I've been to a power plant. I've operated a car. I've got all kinds of situations where I know that I'm taking heat and I am making power. Well, that's correct. And the trick is what makes this possible and realizable in the real world. It says that you've got to reject some heat to a lower temperature reservoir in order to make power. Okay, so the left-hand sketch, impossible. You can't turn heat directly into work. Right-hand sketch, possible. You can turn heat into work, but not all of it. You have to reject some heat to a lower temperature reservoir. And so this is classic in terms of power plants, classic in terms of automotive engines, classic in terms of gas turbine engines. We're purchasing heat somehow, and what we want, our objective as engineers is to create power. Okay, but the second law says you got to reject some of that heat that you bought. Simple as that. Okay. The third statement of the second law, and this is one that I have had the most trouble with. I have gotten better at it. And I'll have to tell you that I did a terrible job when I came back to teach in 2020. And this was the first time I taught out of your textbook. I had previous textbooks from years ago. And I didn't catch on to this very quickly. It took me some repetition to catch on to this statement and this method for problem solving. And now that I've caught on to it, I find that it is an extraordinarily powerful method for problem solving. Okay, third statement of the second law. It is impossible for any system to operate in any way where entropy is destroyed. Entropy is destroyed. So you can't destroy entropy. All right. And so this is sort of my translation of what that means. And we're getting close to doing some stuff in the textbook and helping you with your homework problems and engineering problem solving. The entropy production for any process is always greater than or equal to zero. That's something I've become comfortable with. The entropy production making things more disordered for any process is always greater than or equal to zero. Okay, so new symbol definition. Extraordinarily important. Again, if you get anything out of this video, this is Greek letter sigma. It is not the number 6. I don't know what other letter it might look like, but it is Greek letter sigma, and it stands for entropy production. Not just entropy, but entropy production. Entropy is a property. That's S. Sigma, Greek letter sigma, is entropy production. Entropy that's produced as a result of a process. I'm going to say it again to put you asleep. Greek letter sigma stands for entropy production, not entropy. Okay, so on the last part of this slide, this is a functional third statement of the second law of thermodynamics. This is actionable for you as an engineer. Okay, sigma is greater than or equal to zero for any system undergoing any process. Sigma greater than or equal to zero for any system undergoing any process. Okay. We've just covered the 3 statements of the second law. So if someone, even a professor says, a student, I would like you to tell me the statement of the second law. That's a little bit of a trick question, okay? Because there are 3 valid statements of the second law, and we just covered them. Okay, now, the third one, I hope did not blow your mind. And again, I'm going to have to repeat that it has taken me some repetition to get through this. And that's why I'm creating this video for you. What is entropy production? In other words, Greek variable sigma. What is entropy production? We've got to talk about some details of this before you start calculating. Here's my statement of the second law. Sigma is greater than or equal to zero for any system undergoing any process. There is a big difference with entropy and entropy production. Big difference with that compared to the continuity equation and the first law. And so in yellow, I'm trying to summarize. I've got a lot of words on this slide. You can go back and read the words, but in the yellow, I'm using a closed system as my example situation. What's the statement of continuity for a closed system? The mass is fixed in words. M, well, M1 equals M2. The initial mass equals the final mass. And for engineering problem solving, we call that M. That's the statement of the continuity equation for closed system. Got a bunch of equal signs in it, doesn't it? What's the statement of the first law for a closed system? Q in minus W out. Heat transfer in minus work out equals change in internal energy plus change in kinetic energy plus change in potential energy. Equal sign. Okay. You're getting good at both of these. You're getting good at analyzing both of these fundamentals of thermodynamics. Now, second law of thermodynamics is not an equality. That's the challenge. That's why mechanical engineers get paid the big bucks. Second law says sigma, Greek letter sigma, entropy production is greater than or equal to zero for any process. So in other words, entropy is not conserved. Entropy is not conserved. Entropy is either produced for irreversible processes or stays the same for reversible processes for any process occurring in the universe. That's a true statement. Okay. For classical thermodynamics, for us engineering problem solvers in the real world, that's the way it is. Visualizing entropy. I said some words about entropy, but I tried to devote a simple slide to try to get something in your head regarding how do you visualize entropy. I think of entropy as a measure of disorder. Here's my marbles that are attached in rows and columns. Throw them up in the air and they just go all over the place. That's disordered. Okay. So highly ordered would be a low value of entropy. Highly disordered would be a high value of entropy. Now back to the textbook. This is worth, again, I had such a hard time reading through all the words of the textbook and then turning it into something actionable. I want to cover this with you. Section 523 in your book, made a screenshot. I've added a couple of things. So here's equation 5.2. A bunch of words. That's entropy change. Equals entropy transfer, bunch of words, plus amount of entropy produced. That's sigma. Entropy production. That is Greek letter sigma. Okay. Not going to blast through these words, just recognize well, I hate to say it, don't I? We've got a formula. 5.2. All right. These words do mean something, and ultimately you're going to try to get these in your heads, but it's going to be tough. But three basic terms, at least this you can get an entropy change term equals an entropy transfer term, and last, an entropy production term. At least get that. All right. I have pasted in the exact same equation 5.2 for you here. And what I've done, what I want to do is a visual repeat of equation 5.2, trying to reduce the word count. Okay. So here's our equal sign. Left-hand side, entropy change of the open or closed system equals two terms on the right, entropy transfer, something that's happening across the boundary, that dashed line boundary of your system. Okay. Transferring of entropy. And then finally, sigma, the amount of entropy produced, entropy production that's resulting from the process itself. Okay. The next thing I want to do that really helped me with my understanding, and so it's my hope that this little change will help you with your understanding. There's nothing wrong with the book. The book is fine. I'm just trying to throw out some ideas for you to help with your understanding. What I want to do is take this term and I want to move it to the left-hand side of the equal mark. Entropy production equals. So I hope that I've entropy production sigma is greater than or equal to 0. So I'm making a little note there. Equals. Well, let's get the other two, collect the other two terms. Entropy change, okay, minus, so see how I'm moving this term over to the left. I didn't say that very well, did I? I'm going to keep this term entropy production on the right, and then I'll flip it once I come down to my next equation. So I want to keep this on the right, but I'm going to subtract this term from both sides, and then I'll flip left and right. Okay, so do you see how entropy transfer goes to the left with a minus sign, and then I flip the equation. So I sort of bumbled through that, so I'll repeat it. Entropy production equals entropy change minus entropy transfer. This helps me understand something ultimately that becomes actionable. Entropy production, that's what we're trying to solve for on all our homework problems and our engineering problems. Entropy production equals two things, entropy change of the system and entropy minus entropy transfer. Okay, so now visual statement of the second law of thermo. I've shown it in yellow. Sigma, entropy production is greater or equal to 0. So I've made some statements here. Okay. The entropy produced as a result of any process must be greater or equal to 0. That's just the English words of that equation. It's an inequality, isn't it? Okay, next statement. If the entropy produced as a result of any process is greater than zero, if it's greater than zero, then the process is irreversible. And it's possible and irreversible. Greater than zero. Next statement. If the entropy produced as a result of any process equals zero, if sigma exactly equals zero, then the process is not only possible, but it is considered a reversible process. Possible and reversible. That's if sigma equals zero. Now, more importantly, if the entropy produced as a result of any proposed process, if this is less than zero, if sigma is less than zero, then the engineer can say that process is impossible. Big engineering conclusion. This gives the engineer an ability to say which processes are possible and which are impossible. If a process is possible, there's two possibilities. It's possible and reversible, or it's possible and irreversible. Many real world processes are possible because we see them, but they're irreversible. Okay. I hope this slide helps you keep things straight. Okay, so now what I'm going to do is I'm going to try to dissect as best I can these different terms, these bracket terms. Entropy production, we've covered, we beat that to death a little bit, so okay, this bracket term, the amount of entropy produced, there it is, equation 624. We're getting in chapter 6. All right. The next thing I'm going to do is say some words about these next two bracket amounts. Okay, this is a little bit of a repeat of the previous slides that I beat to death. Okay, here we go. And maybe it's worth repeating. Sigma, it's got to be greater than or equal to zero for a proposed process or cycle to be possible. Okay. If sigma is greater than zero, not only is the proposed process or cycle is possible and irreversible. If it exactly equals zero, then of course it's possible and reversible. If sigma is less than zero, you don't even have to worry about whether it's reversible or irreversible, because it is impossible. It's impossible to achieve whatever proposed process you're proposing. Okay. It's going to be amazing when you get out and start working as a practicing engineer. There's going to be lots of people who are not trained in engineering who will propose processes that are not possible. And you're going to be able to quantify that and explain to them in a respectful way why what they're proposing is not possible. This was one of a major parts of my career, was being able to quantify things that are and are not possible, and then to be able to explain in simple manners, respectfully, why a proposed idea is not possible. Okay, now next bracket term, the entropy change term, capital S2 minus capital S1. Capital S, extensive property. And so this means the change in the property entropy of a system where you have that dashed line thing, okay, the dashed line business. It's changed from state 1 to state 2. So that's simply the that is the extensive property S, okay, for any process 1 to 2. And then a reminder for a closed system, capital S2 minus capital S1 equals M times little s2 minus little s1. That's getting you towards solving your homework problems. Okay, so this entropy change term has to do with the property S that's tied to your system. Change in capital S. The most difficult term to deal with in this entropy production computation is entropy transfer. Okay. And notice it's difficult because it is an integral. and you're having to integrate del Q over T for the process itself, okay, across the system boundary, okay. There are some complications of that, okay, and you have to remind yourself, and I don't want to get into the details now, we're going to probably do this best by example problem, but do recall that in this term, this integral of del Q over T term, Q in is considered positive. Q into the system is a positive number. So if you have a sketch, and there's going to be many sketches in your homework problems where you've got heat flowing into a system and heat flowing out of a system, primarily cycles, heat flowing in and heat flowing out of a cycle, you've got to remember that the heat flowing in is a positive number and the heat flowing out is going to be a negative number. Okay. That's best for me just to leave it right there and let you know that the entropy transfer term is difficult. It is difficult. Once you practice, you will become more comfortable with it, but you must practice at this to get this right. Okay. And the reason, I'm going to go back a slide. The reason that it is critical for you to get this right, the sign, S-I-G-N, right on this term, is remember what you're trying to do is you're trying to evaluate this. This is never given to you. Sigma is never given to you. You're always trying to calculate it. And the only way you can calculate sigma is to evaluate this term and evaluate this term. So if you get this term wrong with sign, S-I-G-N, you're going to make the wrong conclusion on whether your process is possible or impossible. All right. We've made it through your introduction to entropy and the three statements of the second law. So here's our recap. Entropy is a property. It's a measure of disorder. The higher the entropy, the higher the disorder. The lower the entropy, the lower the disorder. There are three statements of the second law of thermodynamics. We just went over them. Sigma, Greek letter sigma, is defined as entropy production. It's not entropy. It's called entropy production as a result of a process. And then an actionable statement for the second law of thermodynamics is sigma is greater than or equal to 0. It's a simple statement and it is actionable. It enables you to make quantitative computations and then make an educated and correct engineering judgment of whether a proposed process is possible or impossible. So that is it. I hope you've gotten something out of this video. A number of takeaways. What is entropy? What are some statements of the second law? And then as we continue on in this series, I'm going to try to come up with modules that quantitatively illustrate the power of second law analyses so that you as an engineer can tell whether processes are possible or impossible. And if a process is possible, determine whether it is reversible or irreversible. So that's the big picture. And the more you work on and solve your homework problems, the more comfortable you're going to get with this topic.